We are here on the 13th of May, Wednesday, for the CSE 455 Software Engineering. I'm excited about our meeting today because this is the meeting before the week where you will deliver your prototype number one. So I hope everyone is ready, including the QA team. Okay, so we'll prepare for that, and I hope everybody is excited as I am to know whether your prototype has passed QA. Okay, let me remind first to you about the deadlines. As you all know, I have completed final reviews of all SRS and SPMPs. So you have obtained all the software requirements from your clients, and you have planned on how to deliver the first prototype, which is what I said next week. So the moment you get my approval of the SRS, be sure to get the client's approval after I approve your SRS. Client, remember, in the agile software development must be involved in the development, and they can change the requirements even up to the last moment of the prototype is going to be delivered. You know the saying, the customer is always right? Yeah, that works here too in the agile software development. That's why we develop it incrementally and slowly, because we want to accommodate every wish of the client. The QA teams, currently, right now, I am reviewing their SQAP, and there could be changes, and they are revising and selecting test cases that they will use to crash your your software project. Okay, so they are not there to play nice to you and say, hey, your project or your prototype number one is working. No, they are there to attempt to crash your mobile app. So make sure you also test your mobile app, because they will try to crash it. That's their mission. And right now, they are planning on what test cases to try. Um, the software architecture and design, I said it is due this week, the 11th to 15th, but I'm extending the very last day to submit your software architecture and design up to the 17th. That's the Sunday of this week. And as I said, coding and designing go hand in hand. So while you are coding, you could be redesigning and then coding again and proceeding forward. So that document won't be due till the Sunday, this coming Sunday, the 17th of May. And as I have told you, next week is the 7th week of our class, and during the 7th week, we deliver the prototype number one, the first iteration, and we'll do it for the whole week of next week, the 18th up to the 24th. Okay, since we have connected together through Slack and Zoom and other online communication system, we can do the testing remotely. Okay, so make sure you are in touch with the QA teams. There are two QA teams, the QA team for Monday and the QA team for Wednesday. So make sure that they get your use case diagrams and all your user interface designs. Okay, so here is the procedure of the QA team, and the QA team will try to follow this procedure. So when you are ready for testing your prototype number one, you need to inform the QA team that you are ready for testing. Okay, so once the QA team has been informed, QA team will access your development repo. So give them access, they can read all your stuff in the repo, and first thing they'll do is check whether all the software artifacts are stored in the repo. So your documents, SRS, SPMP, and the design, software architecture and design, and of course the source code are stored in the repo. If it is not there, you will fail the QA testing. Okay? And then the development team will give instructions to the QA team how to compile and build the executable object module. So the executable will be created by the QA team. You should not help the QA team from doing this. You just give them instructions based on the artifacts you have in your repository, how to create the executable object module. Then the QA team will install the executable object module to a mobile device for testing. Okay, so the QA, if they cannot execute or they cannot compile or build it, you fail the test. So make sure that the instructions are clear and correct and that you have um, tried it first to make sure it runs. Okay, then the QA team will perform testing on your prototype one. So they will tally the the results of the QA testing, and then they will submit a test report to me. And after I review it, a copy of the test report will be given to the development team. So they will know whether they pass or fail. So what's the criteria for passing? The development team must pass all uh, the criteria for test of the test report. They should pass all criteria of the test report. And what are these criteria? Well, number one, they should test your functional and non-functional requirements. So the functional are defined by the use case, the use cases, and the associated user interface to perform the function. And for the non-functional requirements, performance, if you have specified that uh, the software must respond within an amount of time, like 2 to 3 seconds, they should also say that. Usability is the user interface look nice, easy to understood, to be understood, and find out the information that you need. They will have a check mark on the non-functional requirements on their report. They will also check whether the software artifacts is complete and that they perform verification and validation, process. And so during this time, they will see if the team has done unit testing, integration testing, system testing, and regression testing. So they want to see evidence that you did this. And the best evidence is you should keep a copy of the test cases you have used um, as a um, as a proof that you have done all of this verification and validation process. You should collect metrics for your team, like for instance the productivity metrics. The teams should take note of the number of lines of code that the team produce uh, per hour. So you count all the lines of code you have produced from the time you begin coding, divided by the total time you have spent in the project. So that also includes um, the time you spent in design, um, coding, debugging, and anything to do with lines of code, you count that and divided by the total hour, uh, the total time that it took you to produce the code. And the time that took you to produce the code includes the design time and the debugging time. All of that are lumped into this hour. So that will be the productivity of the team as a whole. How many lines of code do you produce per hour? And the quality of the code that you produce is measured in the number of faults per thousand lines of code. So as you are doing your unit testing, integration testing, system testing, and regression testing, count the number of bugs you have um, found and fixed, and uh, collect the number of bugs that you have discovered divided by per thousand lines of code. So you normalize your lines of code into thousands of lines of code, and that will be a metric to measure the quality of your code. I just noticed in this list I missed one criteria for the QA testing report, and that is, did you follow the coding standard? The coding standard has been specified by the QA team, and so you should follow the coding standard. Okay, so if you're using Java, did you follow the coding standard for Java or Objective C? There is also a specified coding standard for Objective C. Okay, so those are the criteria for the basis of the QA test report. Okay, so make sure that you follow them and keep those in mind about the what are the things the QA team is looking for when they start testing your prototype number one. Okay? All right. So let's go back to our lesson of design goals. Okay? So the design goals that we follow for um, in design, how do we fulfill design goals? Okay, so last time, let me make a brief review of what we did last Monday. Notice here that in our design, we start from a component, a software component in the deployment diagram. So in the deployment diagram that you see over here, web server is a component, a software component running inside the hardware that contains the Unix host. And then from here, will be able to use hierarchical decomposition to separate the different components of the web server. And I notice here that you have three components inside the web server. So these are the decomposition of the web server. And in here, the three components are the servlet, the HTTP service, and the DB proxy. But if you're going to use the um, the design pattern MVC, then that's what you're gonna see inside the decomposition of the web server. The model, view, and the controller. Remember that design pattern? So it is consisting of three components. If you're building a website, you the user inputs his uh, inputs data or inputs information through the controller, and the controller access the model, and the model is changed, and, and when the model change, it informs the view. The view will change the the graphics or the data that is displayed on the screen. And the three component system, MVC, is a standard design pattern for building website. And if you have a chance to use it, use MVC, because languages support that framework. And we talked about it last time. PHP has a framework uh, called Laravel, and Laravel is used in our Babylin applications. That is CHAS Masters project. Okay, there are two symbols that you see over here, the ball and socket. And the ball is a symbol that it provides a service for any component wanting to use your component. So it has a service that it can provide, and the socket on the other side that as you see over here is the symbol that it needs a service from other components. So the socket is the symbol for that. But the idea that I want to um, emphasize here is that directly from the deployment diagram, you can begin your architecture by detailing a software component that is in the deployment diagram, and you detail it using whatever means design, architectural design that you have in mind. So in this case, the web server component is detailed or is decomposed into the MVC design pattern. Okay, so directly from the um, deployment diagram, you can start your design. And we have here um, another deployment diagram, and we have software components, routing subsystem, and the planning subsystem. And on this deployment diagram, hardware is embedded into another hardware. And this is a representation of a trip and a planning system to have a driving trip to a faraway place, and you want to find out how to get there, and also the places to visit while you are on your trip. So the car here is the hardware represented by the web host, and inside the car there is a web server using Apache, and the software that runs there is the planning subsystem. There is also another onboard computer that is um, running running the or having a software component called routing subsystem, which it gets information about routing. So this could be a map like Google Map that you usually use, and the onboard computer is actually giving you the routing subsystem in there. Okay, so here is the hierarchical decomposition of the routing subsystem. It has four components right here, and the planning subsystem has six components. And you discovered another software component called communication subsystem. Well, the routing subsystem and the planning system must communicate with each other. And that is why communication subsystem was developed. Okay, and then other software components are identified, and these other components are the trip file store and the map db store. And the reason for these two other components is how to keep persistent objects. So you want your routing trip stored. That is when you shut down the uh, your uh, uh, your onboard computer, it's still there. You can retrieve it and look at it. And the map database store for the planning system is also kept, so you can look back and try to uh, retrace the trips that you had, and maybe you want to backtrack and visit another place. So those are things that you need when you try to um, uh, get previous information of your trip. Okay, so we talked about last time about the use of flat files, relational and object-oriented databases. So um, flat files are huge and may have anomalies in terms of uh, repeated information, or when you are trying to delete, you might delete important data, which is very bad in a database. But flat file is the simplest of all the database design. I would recommend relational, where you have tables, um, several tables containing information, and you access the data through a key. And when you want additional information, not directly obtainable from the tables, you join tables to find that information. So it stores the data efficiently, so you don't have that massive data as in a flat file. And through join operation, you can get other information as well. It also has concurrency, uh, that it supports multiple access to the database, and so you leave the data in good integrity, then allow, if you don't control the multiple usage, you will leave the database in a state that is not consistent. So concurrency is a synchronized access of the data and ensures that only one process is accessing the database. Okay. Now in the system of the routing subsystem and planning subsystem accessing the communication subsystem, notice here the lines of connection let me show you that. The lines of connection to the communication subsystem is now replaced with, instead of dotted lines that you see here, okay, we replace it with a much more meaningful link instead of these dotted lines with a arrowhead, okay? So the meaning of this symbol is that, as I have said, the ball means it provides a service, and the socket means I need a service. Okay, so that gives you more information in the graphics that there are software modules or components that would need um, data or need service from other components, and others that provide the service. So the communication subsystem that you see over here provides the communication um, between the routing subsystem and the planning subsystem. Okay, so the communication subsystem symbol are balls. These are balls, means I provide service for you, while the socket represents I need service from other components. So they kind of fit each other. Ball and socket uh, fit each other, and in a connection, ball and socket means it's a tight communication between two components. So you can use that symbol to represent tight communication protocol between the components. Okay? All right, so continuing there, we have another example previously. If you remember the arena um, mobile app or application is used to arrange for simple games like tic-tac-toe or chess game, and the arena deployment diagram, as you see here, consists of two hardwares, the server machine and the user machine. Okay, and inside the user machine, you have two software components: the arena client and the match front end peer. If you remember that problem, we have um, a league owner who must arrange for uh, for for people to join a league. Let us say you are an ardent tic-tac-toe player. You want to form a league of tic-tac-toe players. So, of course, the league owner will have to advertise and look for sponsors of the tournament. So it will need a system to first organize um, the game, and the other for the game itself, how to manage the game. And so there are two separate design goals, one for managing the game and the other for organizing. And um, the hardware software mapping in the UML diagram consists of these software components. So for the user machine, you will have the arena client and the match front and peer component. In the server, you will have the arena server, the arena storage, the advertisement server, and the game peer. Okay? Remember the two design goals. The design goal for managing um, the organization, and the other one is managing the game itself. So first, we try to design for the game organization. So how do we organize the game? Okay, I remember in the game you have to manage the different teams that are playing, and so the architecture that was chosen in here is the layered architecture. Remember the three-tier architecture. The lowest layer is the storage. So this is where you keep all the information about the game organization. So the arena storage, if you recall, that is the one of the software component that you have over here. The arena storage was identified as the one of the software component, and the arena server was identified as one of the software components. So in here, you will see that um, the uh, three-tier architecture is given. So you have here the storage, the arena storage appearing here as the lowest level uh, layer. So anything about storage is done in here, okay? And on the top, which is the application, is the arena client. And the arena, this layer here, contains the interface, okay? The interface for the arena client. And arena client is identified here as one of the software component right here. So arena client, arena server, and arena storage are found in our three-tier architecture. Arena client, here is the arena server, and the bottom lowest part is the arena storage. Okay. Now inside the application logic, you have the following components inside the application logic. So besides the arena server, you have different management um, modules in the arena server. First, the user management that should manage the user who is accessing the system. The game management who is actually accessing the game itself, tic-tac-toe or chess game, how do you manage the game. The tournament management, that you have to manage the winner through a like a round robin kind of information or tournament running of the tournament. And of course you have to earn money through advertisement. So there is the advertisement management. So and then of course there is the notification. The notification is the your interface to the arena storage, where to store the information in the storage layer. Okay, so if you look at the original uh, deployment diagram, we have the advertisement server and the match front peer, and the game peer were not did not appear in the game management or game management part of the design goal. So, but we identified other components that is important in the accomplishment of the game organizational part. Okay, so right here is an example of um, a architecture derived from the deployment diagram, and we apply the three-tiered layer architecture. So remember the rationale of the layered architecture. You separate the different concerns in a three-tiered architecture. The lowest layer is the storage where information is kept. The top layer is the interface that interacts with the user, and the middle layer contains the application logic. So very powerful architectural style in the layered architecture. So here is the example of the three-tiered uh, architecture. There is also a four-tiered architecture if you need to split the middle layer into two layers. Okay? All right. So the next design goal is how to manage um, the game playing part, the game playing part. So the game playing part, so the first one is the organization of the game. The next one, clients and advertisement and so on. And the next one is the game itself. How do you manage the game itself? So you have a tournament management component that you identified, and the match front end peer, the game peer, the game management, and the advertisement management. So the uh, at the top um, original deployment diagram, we have the match front end peer. So this is the match the match software component that manages the front end peer. And we have the advertisement server, because we need advertisement to support the game itself, and the game peer. So out of those components, we use a game peer. This is the component that manages the game itself. The match front end peer, and the advertisement management. So the advertisement management there is the same as the advertisement management that you have over here for the game organization. Okay, and they appear in both design. And the game management itself, game management does not appear in the deployment diagram. It was added to the design because of the need to um, manage the game itself. Okay, so you can see the two design goals that were um, developed here. One for the game organization, how to game is organized, and the game playing itself, how to manage the game playing itself. Okay, so here the architecture that you see over here is um, um, what we call decomposing into subparts. So divide and conquer. So divide and conquer, you have five components making up the software design, and while the game organization, the architecture style that was used is the three-tiered architecture. Okay, all right. So let's continue to the next topic here of um, uh, uh, game design techniques that you can use, or architectural style that you can use. To the addressing design goals, let's look at the um, example I created to show um, how to use um, hierarchical decomposition, tiered architecture, MVC, or client server, repository, all those kinds of architectural style that you can use. Okay, so let's say we have a um, deployment diagram that you see in this drawing here. We have two hardwares, and the hardware contains two software components, A and B on hardware number one, and E and D in hardware number two. So we can start our architectural design by uh, detailing, let's say, component B, software component B. So using hierarchical decomposition on component B, we have two subcomponents that we have identified called B1, B2. As you can see here, B was decomposed into two sub-components, B1 and B2. Okay, and then after that, uh, we uh, um, we are able to derive the class diagram of the B.1. B.1 component is now detailed as a class diagram. So at this point in time, I am able to detail the B.1 component into each class diagram. Okay, so you see here, you have B.1.1, which is a superclass of two subclasses, B.1.1.1 and B.1.1.2. Okay, and then from there, I'm able to um, write uh, pseudocode of the class B.1.1.2. So here you have the list of member variables, and I have member functions or methods F1 up to Fn. And then from there, I detail the function in pseudocode of those methods that are critical to the operation of the class. So here in this example, I detail F2, and F2 has parameters X, Y, and so on. And the pseudocode is written. So remember what I said before, you don't need to write it in a programming language. You can use pseudocode to express the logic of F2. And the reason for that is I can check the logic of the pseudocode without dealing with a compiler to compile my code. My aim is to make sure the logic is correct. So another function that I think is important is fk. So fk has parameters u and v, and the pseudocode is also written. So you don't need to write the pseudocode of all the other functions, only the important ones that are critical to the operation of the class. Okay? So continuing on, we can um, detail the software component D in terms of three-tiered architecture. So you see here, three-tiered architecture, D.1, D.2, and D.3. So in other words, what I can do is for each software components that I have in the UML diagram, I can come up with the decomposition of the software component into whatever architectural style that I see fit. So in this case here, I have packages, and inside packages are components or subparts of the package diagram. And so, you know, in the package diagram decomposition, I can detail it either with other package diagrams uh, or class diagrams if I am able to determine the detail of that package diagram. Okay, so here is the hierarchical decomposition that was used in component B, and for component D, I'm able to use three-tiered architecture. Okay, so next one is the component E. So component E is a web server, and therefore I can identify and use MVC. Since MVC is well known to work for web application, I can use that in my decomposition of uh, the software module E. And so, of course, not shown here are additional um, components that in your analysis is added to your design, depending on what is your design focus. So other components could be included in your analysis. So right now you see the total decomposition of the software architecture um, from the um, deployment diagram. Now, what you need to do is identify uh, which is high-level design. So this represents high-level design. So if you use component diagrams or package diagrams or modules, as you can see here for MVC, then this constitute high-level design. So the high-level design just identifies the different parts of the software without detailing what is inside those components, what is inside that module, and what is inside that package. That's high-level design. Okay. Now, the moment you identify class diagrams, like here, now that constitute low-level design. So the low-level design constitute class diagrams. And the class diagrams are, of course, represented by classes or objects. And inside the class or objects is the name of the class, the parameter, the data variables that it used, or called member variables, and member functions or methods. The moment you identify the class diagram, that constitute level design. Okay, and then when you detail each of the class into its uh, functions in pseudocode, that's what you call detailed design. It is a very good technique to actually use pseudocode rather than source code. And as I have mentioned before, the pseudocode is used to actually analyze your functions if it is able to perform the function it's supposed to do by doing a paper tracing of the pseudocode. And if you do that, you will um, uh, you can determine errors in your logic or pseudocode, and and you don't need to and the error that you or fault that you discover will not appear in the source code anymore. That's the idea. So if you fix it in pseudocode and the pseudocode performs correctly in your paper trace, then the probability that the source code that will be produced will be correct. All right? All right. So next thing that we need to um, uh, next thing that we need to do is have a example of a reverse engineering. Remember what I told you about continuing the work of a previous team. Now, some teams may not have left software architecture and design documents for you. So, in order to complete the work, you have to derive the software architecture and design of the previous team. And since it is source code, I am assuming the source code are in terms of class, classes, and the class are defined and they are given as a source code. So the first thing you need to do is to um, convert those source code into class diagram. So here is an example of a class diagram. So you you see a code called order, and here are the variables, and here are the member functions or methods, and here is a superclass subclass um, representation, the customer, and the corporate customer and personal customer are the subclasses. And then there is this employee. Employee is another class that associated with the corporate customer. And over here on the left side is the order line and the product. So product is a class. Okay. So what you can do when you see source code is try to draw the class diagram with the corresponding communication or association between each of the um, classes. Okay? And then you look and review the function of each of these classes. Okay? So customer, corporate customer, personal customer are related to each other because of the subclass, superclass. So remember, your criteria is called cohesion. For a good design in object-oriented design, you must have high cohesion. The high cohesion means it is related strongly to each other, or they perform a function that is um, they collaborate in order to produce that function. So in this particular case, I have identified the classes. I did the class diagram, analyze it, and draw the associations, communication lines between them, and uh, and then look at the cohesion of all of these classes that I have. Okay, and this is what I came up with. Okay, so uh, I analyzed that this classes, customer, corporate customer, personal customer, and employee are all related to each other. The cohesion is very high. The relationship of each of these classes are high, and therefore I enclose them in a group of classes, and here is what I have. Okay. On the left side, I um, I look at the um, I look at the left side, and here I see order, order line, and product. Okay, so I figured that order and order line are related to each other. Okay, so the order is the big uh, detail of the order, and the order line is one line of that order. So I concluded that these two classes are related to each other. So I enclose them as belonging to the same group, the order and order line. The product is kind of different. It is not an order or order line, it is the product. So I decided to group that into another component, okay, or package. And here is what I got after I enclose them in three groups. As you can see here, um, the bunch of classes I have reduced into three uh, packages, and inside those packages are the class diagrams that I have before. So you can actually go through source code that you inherited from another team and kind of draw boundary lines on classes that are related to each other, either by inheritance or they perform a, um, a specific function that they all help each other to produce that function. And once you determine that, enclose them into boundary lines and then call them um, packages. Now, packages, if there are resulting packages that are um, quite numerous, you can again merge those packages together to form a bigger package than before, thus reducing number of uh, packages that you have until you have a, a number of packages that can be viewed and understand what the overall function of the software. So try using that in those projects that didn't have um, any architecture or design, and then when you after you have drawn the package diagram, you can add your own package diagram and identify it with a different color of ink. So the dark ones are the previous one, and the colored ones are the ones you have added. So next team that would inherit your work could see what was there before and what was added by your team. Okay, so that's what I would recommend for reverse engineering the source code that you have inherited, since I will assume the source code are written in terms of classes. You can actually convert these classes into class diagrams and then grouping the class diagrams into packages. Okay? All right. So I end my lecture today, and keep and be safe, and be healthy. I'll see you next week. Bye bye.